Good evening, ladies and gentlemen. I'm Pasang Fernando, representing the board of Sri Lanka Energy Managers Association. And on behalf of the SLIMA, I take pleasure in warmly welcome you to our 70th Energy Management Advanced Energy Efficiency and Conservation in Centrifugal Pumps and Systems. Today, our resource person is Mr. Dinesh, who's Chief Engineer at National Water Supply and Drainage Board, who is also an energy management expert of UNIDO and also a centrifugal pumping system expert. Mr. Dinesh holds BSc from University of Moratuwa and MSc in Energy in Circular Economy from Open University, as well as MSc in Sustainable Energy Engineering from KTH and the Master of Engineering from the Open University and Postgraduate Diploma in Energy Technology from the University of Moratuwa. Mr. Dinesh has more than 20 years of experience in water supply, pumping system design, installation, testing and commissioning, and in designing of energy efficient pumping system, energy auditing and energy management. Now I take pleasure in inviting Mr. Dinesh to conduct the presentation. Mr. Dinesh, the floor is onto you, sir.
Today we are going to discuss the energy efficiency and conservation in centrifugal pumping system, right? That we have little, I think that it is huge, that topic, but we have limited time. Then that we can go through quickly. That you know that the pumping system generally account for 22% of the world electric motor energy demand. That it is a very huge amount. That then come to the centrifugal pumps. That it is about 73% for centrifugal pumping, right? Then 73%. Then it is that importance of energy and conservation in centrifugal pump. Then if you just come to the introduction, that centrifugal pumping system, that basically I just going to describe that centrifugal pump. We have this pump curve, right? Then very important one, you have to, I think most of you know about the pump curve, that we have flow rate this side, Q, then basically head main that the pump can deliver the pressure. Say head and pressure both are same, but head we generally in meter, but pressure very depend on Pascal or bar or whatever it is. But for centrifugal pumping system, we use this term meter head. Then this is pump curve. Then we have system curve, and we have operating point, right? Then this one is very important one that you can see here. This is the efficiency curve. Then that efficiency, pump efficiency is going to vary depend on the operating point. If the operating point is somewhere here, then pump efficiency is optimum, maximum. But depend on the operating point, that pump system efficiency is going to affect, right? Then important one is this operating point and best efficiency point. Then according to that, we have another curves, pump power curve, NPSH curve, and it is not related to, actually related to energy, but we cannot go more detail on this curves, NPSHR and power, but we have to think about the operating point and best efficiency point. Then this head. In general, we have head curve and efficiency curve and power curve and NPSH required curve. This is basic centrifugal pump curves. We call that you have to have understanding on this before before think about the energy conservation. But this is very important when you are going to select a pump. In PSHR is a very important one, but we are not going to cover this one in this section. But you have to keep in mind these are also important, right? Then if you think about the pump curve, we have, say, this is called shut-off head, then base efficiency point, and maximum flow rate we normally call run-out point, right? Then we have this sort of thing in basically in pumping system, right? Uh, Again, I am telling this system curve and pump curve, that intersection point is duty point. You have to keep in mind that duty point is always not the base efficiency point for centrifugal pump. That is the one thing that in energy conservation, uh, this inefficiencies is there due to uh, mismatching and base efficiency point and duty point. Right. Then if you come to this one, uh, then system approach is very important when you think about the centrifugal compensation energy conservation. Then generally we have electricity utility feeder, utility supply. Then we have transformer, motor breaker, starter panel, and starter. Sometimes we have VFD. Then it's come to the motor. Then coupling, that pump, then fluid system, and ultimately we have deliver pressure, required pressure and required flow. Then this is that each and every step we have inefficiencies, right? But our scope is generally this, that transformer, that if it is I3 category, we have this one also, transformer also included. But generally I1 or I2 system, our system is, we have to consider this motor breaker, starter drive, motor, coupling, pumps, fluid system, and ultimate pressure, right? Uh, then, then if you come to this centrifugal pump in operation, generally what we do is we deliver that pump develop head and flow rate. Then what pumps do? Develop a head and give required flow rate. Then to do this one, this is called uh, water power delivered by pump. Then to do this one, we have to rotate this pump shaft, drive the pumps, right? Then this each and every equipment, say pump, we have that efficiency. Then to run this pump, we need more than the total power is say P. Then we need more than P to run the pump, right? Then we have motor shaft coupling. Then we have shaft power. Then electrical power, electrical input. Then general idea is this, that pump how it's work, right? If you come to that energy conversion, then this equation is important. Is that water power out is that flow rate, that flow rate should be cubic meter per hour. Then specific gravity for water, it is 1. Then H system head is in meter. Then the P for this water power output is, we can calculate by using this equation. Then it is W, right? A very simple equation, flow rate into H, that flow rate should be in cubic meter per hour. Then H should be in meter. Then specific gravity is water points 1. Then divide by 367. Then we can calculate what is the water power out. In any case of centrifugal pump, we can, if you know the flow rate and if you know the head, then we can calculate this power output, the pump. Then if we divide by this pump efficiency, then we can calculate the sharp power pump in power. Generally, it is direct coupling. Almost we can consider as 100% efficiency. Then P2, the direct coupling P2 equal P1. Then P1, that motor efficiency, if you divide by the P3 by motor efficiency, then you can get this input power. Then finally we can calculate overall efficiency is flow rate into head into specific gravity divided by 367 divided by power in. This is the system overall efficiency, right? It is important to calculate before start your work. You have to know that what is the efficiency. Then this sort of thing you have to do very easy one, easy calculation, right? Then if you come to this very important one in energy conservation, specific energy consumption, we can SCC. That means specific energy consumption mean kWh per cubic meter. To pump 1 cubic meter, how much kWh required. Then if we simplify this one, overall efficiency equal Q H system. This one you know already. Then we simplify this power in divided by Q. Then the H system SG divided by this one will come, right? Just simple calculation, right? Then this one is then specific energy consumption, SCC. Then you can see here SCC is H divided by 1067 and overall efficiency. If we simplify this, H mean that system head is always we have uh, static head plus friction head. Then it is static plus friction. Then SG. This is simplified 261 pump efficiency, motor efficiency, and starter efficiency. Very simple. If you that in energy conservation, what we have to do is we have to reduce this specification. That is the ultimate goal in pumping system. Anyway, if you can reduce the SCC, then you can save energy, right? Then this is the basic equation. Then if you want to reduce this SCC, then you can see here you have to reduce H static, you have to reduce friction, and you have to increase pump efficiency, you have to increase motor efficiency, and you are going to increase starter efficiency. That's all. Very simple. If you want to save energy, that you have to reduce static and friction and increase pump efficiency, motor efficiency. So that's very simple. But the problem is how we can do this one in practically in centrifugal pumping system. Right? Then this one is I think understand, and you can ask question in later. Then if you think about that system pressure, is very important one. This one always if you want to reduce SCC or then the system pressure requirement is very important. If we can reduce this one, we can save huge amount of energy, right? Then if you think about system, we generally have open system and closed system. That is a piping system. This is if you have overhead tank. Then this is we have static head. That we have sometimes we have closed system. The example chill water circulation system, chill water system or something. This is pump into overhead tank, right? The two system we have. Then that system that we need the required flow rate, here that head is somewhere here, right? Then important one is system curve and what is your system head, what is your system head requirement, and how to reduce this system head, right? This directly related to the specific energy consumption. Right? Then if you think about this system curve, this is static head HS, then this is HF, right? Most of the cases static head, we cannot reduce static head sometime, but if you say if you, in the waterboard context, we can just shown in or something, and we can reduce HS if you think we can reduce HS also, but important one is HF. How to reduce this HF? HF basically we have two component, H major and H minor. Major mean that pipe friction. Minor mean component like valve, bend, something like that. Then we have this two component. How to reduce this major part? We can reduce definitely by increasing the pipe diameter. We can reduce if its diameter is higher diameter, then friction is less. Then you can reduce your system head if you change, if you select the uh, higher diameter. Then you can see here that what is the limit. That is the important question. What is the limit? What is the optimum pipe diameter? One question is there, right? Then if you can reduce the if you can increase the diameter, then reduce the friction. But if you increase diameter, capital cost is going to uh, high. Then we have to have a optimum pipe diameter. To the everything is in cost effective, should be cost effective. Then we have to think about the optimum pipe diameter. Then friction, that if we think about the component minor losses, then say we can say use radial bends, radial tees, and instead of this general bend, we can use radial, and that k value that we have k v squared over 2g generally. Then this is the component loss. Then k value you have to select less k value component. Then we can save the friction head, and we can uh, optimize the pipe diameter, and we can save the energy. This is one important thing in energy conservation system head. Then say for example, then capital cost and friction for waterboard example here. You can see here that capital cost is increasing with the pipe diameter. The capital cost is increasing. Then you can see here friction loss also decreasing. Then what is the optimum pipe diameter is the question, right? Then you can use these formulas and calculate the energy and payback period or something, and you can optimize the pipe diameter. Then generally what we do is that we calculate, then this is say this is capital cost, then this is energy cost, this is the total cost. Then we have curve shape like this. Then we have optimum pipe diameter, then you can select the optimum pipe diameter using this, and you have to keep, I can share this Excel sheet if you want. Then you can calculate everything, energy cost in pumping system, pipe diameter and selection, right? Then we have Excel sheet. Then if you come to this pump, then you can see here, then you know now that friction and head, the system head, we can reduce using this arrangement. Then if you come to pump, then centrifugal pump, there are pump times, in suction on bearing pumps, in suction close couple, in suction inline pumps, multi-stage pump. There are a lot of pumps type. Then general arrangement of pumps. There's nameplate. Then there are RPM, flow rate, head, and everything. MEI values, pump efficiency. You can see it's mentioned in the pump nameplate. Then pump performance curve is like we already discussed. Then system curve already discussed. We have duty point, base efficiency point, and drop in that if the efficiency is that duty point is vary in the system, that efficiency is dropped, and power consumption also increase. Power increase, efficiency drop, depend on the base efficiency point and duty point. Right. Then pump family curves we have. For general pumps, we have family curves. This is higher impeller diameter. Then you can choose your impeller diameter and system curve. Then you can select your pump as per your requirement. You have to provide your head and cube basically to select the pump. Then accordingly, they provide the pump manufacturer provide what is your impeller diameter, right? Then that is one thing you have to keep in mind. Then we have pumps system. They have family curves. That mean it is if the case housing is same, but pump performance may be changed. That's a very important one. Yeah, we just look at the pump. We cannot say what is the performance of this pump because sometimes one pump has higher impeller, same housing, same appearance, but other one is have another performance. That two pumps are not identical, always not identical, right? It's depend on the diameter, impeller diameter, right? Family curve. Then we have uh, RPM curves. Then the pump curve is here. Then we can change the pump curve by reducing the RPM, right? The general VU VFD drives. Then reduce this RPM. Then your duty point you can change by VFD, right? The important one is that your system is somewhere something like this. That people are thinking always if we use VFD, then it is energy efficient. We cannot say that directly. That if your system is, you can see here that pump efficiency is somewhere here, right? 83. That if you reduce the speed, but your pump efficiency may be decreased. The duty point is somewhere here. This is ISO efficiency curves, right? Then the ideally that ideal system, the VFD application is good for that closed system, right? If it is a system curve is flat, generally not accept the VFD application, right? You have to keep in mind that that also is important one, that VFD suppliers, and they said always we can save energy by using the VFD, but it is ideal when only that the system is closed system, then its ISO efficiency curve is changing very equally. But if the system is flat system curve, then our efficiency may decrease that power if we are after VFD installation, that power energy consumption. Maybe I have that experience. I installed VFD in very beginning in my life in 2008 or something. Then in a power consumption was higher. Then I start to learn. Then I finally understand my fault is this. I select wrong system, wrong VFD application, right? Then you have to keep in mind that also. Then if you come to this impeller types, important one is this NS, specific energy, specific speed that you can see here. Depend on the specific speed that pump efficiency is there. Then important one is you have to select correct specific speed for your application. Then only you can select the best efficient pump, right? The important one, that is specific speed. The specific speed equation is this: Ns equal RPM flow rate head, right? Important one is this flow rate is please okay. The head is, this one is per impeller head, very important one. You have to keep in mind this head is per impeller head. If it is the head is 50, if the one impeller, you can use that head as 50. If it's a multi-stage pump, if it's two-stage pump, then you have to use 25 for this equation. You have to keep in mind that. Then you can before selecting the pump, then you have to calculate the NS, right? That very important one is NS. You have to keep that NS in between. Generally, uh, uh, you have to keep the NS in between 30 to 60. It is general idea, right? Then you can select the best market available efficiency pump. If you choose this NS, say NS, you can change NS by using this. You can change RPM, then 3000 or uh, on 50. Then you can change that NS, and you can select your pump, the RPM, and you can change the NS. Then you can change the number of impellers, and you can optimize this NS, and you can select the uh, pump, right? Then the most very important one is people don't know, that engineers don't know what is the market available efficiency, or that we cannot say for pump per pump always that more than 50, or sometimes some pumps may say, you see here that some some pump application we can achieve about 90% efficiency. Some pumping application we can have only 50 efficiency. That is it, you can see here, it is dependent flow rate and NS, right? Then we don't know, actually engineers don't know what is the achievable efficiency for that your specification preparation, right? The very important one that already there is a equation that I take from this standard, EN standard, already develop a equation to calculate what is the achievable uh, efficiency of a centrifugal pump, right? That here you know that NS, you have to calculate the NS, that Q base efficiency, and that's all. And C values, right? Then important one is you can calculate before, you know, you can uh, have idea before selecting a pump what is the achievable efficiency. Then this is that C values, that my recommendation is at least your MEI value, the C value should be greater than 0.4 MEI, right? Then this is here C value. Then you can calculate the what is the achievable efficiency. right? Then pump for pump. Then motor, you most of the day know motor, induction motors, three-phase motors. Then motor nameplate. This short-term is there for selecting a pump motor insulation class, very important one, and duty class. That is on duty or is two duty. Then speed two pole, four pole. Then IP rating. Then service factor and motor efficiency classes. Then generally that at least we have to go for IE3 and IE3 or IE4. Then you can have better efficiency in motor. That if we think about the motor, then the motor load factor also important. That in my experience, most of the cases in energy auditing, that motor is uh, higher capacity motor. I experience sometimes that motor selection is wrong. Then you have to select the motor accordingly, right? Then we can discuss this if you have question. Then if you compare the motor efficiency, then IE1, IE3, IE3, you can see here. Here huge difference in IE1, IE3, and IE4. Then definitely we have to go for IE3 or IE4, right? Then that if we think about life cycle cost, that's a very important one. Then 9 to 1 wattage if it's high capacity motor, then 91% is from that running cost, right? And then the energy efficiency is very important when we are going to buy a pump. Then operation and maintenance also important. Then generally, if we unmaintained pump, that efficiency goes down. And if you maintain properly, then you can achieve this increase your efficiency, right? Frequently you have to maintain the pump, right? Then this one is important. That my experience is most of the cases they are continuous running. They are not think about the maintenance aspect. Then generally that pumps degrade. You have to keep in mind. Then pump curve shift with age, and power requirement is going to high, and then efficiency also going to low. Then the important one is this one, because this motor selection, at least that generally we buy a pump to use more than about 10 years, right? Then within this 10 years, you have to keep in mind that the efficiency is goes down. Then you have to select the motor at least 1.1 greater than the power requirement at the dew point or total pump curve. Or you have to keep in mind. If it is it's very close to the sharp and power and motor power, then future you have in trouble, right? Uh, then energy conservation is pumping. That already we discussed this one. Then my experience is pump is oversized. Then supply and demand is not matching. Wrong pump selection, wrong drive selection, due to point and base optimized variation, wrong insulation, pipe diameter not optimized, poor suction. Important one is poor suction performance, poor controlling. This sort of thing is there when if you come to the energy uh, conservation, you have to think about those things. Energy waste that more head than required, more flow than required, less efficiency. Then say this one, if the this is pump curve. right? This is our selection point, right? Then Q. This is head. It's a APC. It's our requirement is this one selection, but our required Q is less. What we have to do, we do what we control the valve and energy losing energy. Right? If your valve throttling is losing energy, if its head is higher than what is required, then our design point is somewhere here, but design point is here, but actual head is somewhere here. Then definitely that pump is energy consumption is high, as well as efficiency is drop. This efficiency curve is something like this base efficiency. Then if the head is more head than required, then less efficiency. That the reason is not properly select the pump, that they didn't consider the specific speed. Then definitely come the less efficient pump. Right? Maintenance problem is there. The valve throttling on knob control. Right? This one also important. You have to keep in mind that always continuous pumping is the best efficient system. Right? On-off controlling is not efficient. The reason is that the system curve is here. Then continuous pumping is somewhere here. But if you go on-off controlling, definitely that flow rate is higher, then head is higher. Right? Then you have to keep in mind that continuous pumping is the best option for energy conservation. Then controlling, that we have bypass control, valve throttling. The short of controlling is there, but we generally, our suggestion is my energy in terms of energy conservation. VFD is good option, that for uh, closed system, ideal for closed system. That mean not flat system curves, right? Not applicable to flat system curve. It should be this closed system, like VFD application. Then another thing is we have to consider in controlling. Then we can have impeller trimming or diameter, reduced diameter. Then our system is there. That our actual flow rate is somewhere here. And we can VFD application, we can reduce RPM and achieve, or we can trim the impeller and we can achieve this flow rate by efficient way. Right? Two options. Then another one is most of the people forget it. For the flat system curve, the flat, if the system is flat, then to control, if the system is flat, best way is parallel pumping. One or two or three pumps. Parallel pumping is the best option. That efficiency is not going to, the system is, if the system is flat, almost duty point is, the parallel pumping duty point and single pumping duty point are same. Then the efficiency, single pump efficiency is not going to change, right? Then for flat system curve, ideal parallel pumping. For steep system curve, that ideal VFDs, right? And VFD or impeller trimming. Then control valve throttling, energy loss. Then bypass, also energy loss. On-off also energy loss. This is not recommended for in terms of energy conservation. This controlling methods are not recommended. Then valve throttling. If it throttle the valve, then you can lose this amount of energy. Then if it is bypass control, then you lose this amount of energy. If it is on-off control, you lose this amount of energy. Then affinity loss, you can search here that in internet that VFD drives and impeller trimming. Then if we then this if we change that, then the system we change by not while throttling, then we can save energy by VFD application or impeller trimming or parallel pumping, right? Energy auditing that you need equipment, pressure gauges, power analyzer, flow meter, this sort of thing. Then you have to take measurement, very important one. That's calculation, power calculation. I've already mentioned that pump head is. Keep in mind head is suction delivery minus P delivery pressure minus P suction pressure. This is head pump. Then flow rate we can measure directly from flow meter. Then you know the head and you can calculate the power from power analyzer. Then you can calculate the efficiency, overall efficiency. You have to keep in mind that we can have overall efficiency in energy audit. Then system curves we can draw practically. Then energy loss calculation is valve throttling. Then before valve, that is valve throttle. Then here we can measure the pressure. Flow rate is somewhere here. Then measure PD and P is it PD minus PB minus PA is the pressure loss in the valve. Then that turned into flow rate divided by 367. You can calculate the valve loss using this equation. Then you can quantify the what sort of amount we can save by this removing that valve throttling. Then ideally that VFD or introduce VFD, then you can calculate the energy saving and what is the payback period for this one, right? Then I think my time is over. That you can discuss more about that in any question you can ask.
Of course, Mr. Dinesh. Thank you very much, Mr. Dinesh, for your insightful presentation. And we gathered so much insight from you. And of course, I'm sure the audience will have a lot of questions for you. And audience, please, if you have any questions, please direct them into the chat box or Q&A. And the Q&A session will be moderated by Professor Migara Lianage, Joint Secretary of the SLIMA. Professor Migara, the floor is up to you, sir.
Okay, thank you very much, Pasan, for providing me the session for moderation. And thank you very much, Mr. BGA Dinesh, for that interesting presentation. I think you provided a lot of practical aspects of centrifugal pumps and certain aspects related to energy efficiency and energy consumption, and what we could do to improve energy efficiency. So now I would like to request the audience to provide your questions. You can type your questions in the chat box and send to me. I have received one question to start with. So the first question is, please explain suitability of VFD with examples of applications.
Like that I explained earlier that system curve is important one, right? That before you are going to select the pump or starter or whatever it is, then you have like that I explained earlier this that system curve is important one, right? That before you are going to select the pump or starter or whatever it is, then you have to draw the your system curve, right? Then if you draw the system curve, then you know your that requirement flow rate at duty point, say flow rate and head, right? Then that if generally for constant flow rate we need not to have a VFD, right? But in term of that we want that variable flow rate, then you have to know what is your flow rate requirement, say variable flow rate range or what is the flow range. Then if you know this flow range, then you can see that that ideally if you select the pump for this point, this maximum point, this is our pump selection point. But if you change that pump curve by VFD, then our system is somewhere here. But ideally, uh, this is the ISO efficiency curve. Then this efficiency curve, if you use this one, this efficiency is different. This one is higher. Generally, that our selection point is higher efficiency point, but actually that variable flow rate, that point, that efficiency is somewhere here, right? Then you have to think that what is our say, then what is our flow rate, that what is the frequently we use this one, or what is the average flow rate, or then you can see what is the difference in this flow rate and what is the efficiency drops if you use this one. Then you have to judge, you have to take a judgment, and you have to go for, if it is that instead of this one you can go for parallel pump, this one is somewhere in parallel pump, then you can see that what is the efficiency in the you can compare. You have two option, VFD option and parallel pumping option. Then you can see what is the parallel pump efficiency, what is the VFD efficiency. If we use which one is better, then you can select. Actually, you have to select the option, and depend on the capital cost also you have to consider. But if it is system is very flat, then definitely you have to go for parallel pumping, not VFD. If the system curve is steep, then definitely the VFD is the good option. Right, you have to keep in mind this that your flow rate should be vary and your demand. Then only we have to go for VFD, right? That generally what about we go for the VFD as if it is a constant head or constant flow pump. Also we go VFD to reduce the generator capacity, right? Other than that, we needed to have the VFD for constant flow rate. Right? I think it's clear.
So I think you explained it very well. So the next question is, please explain the magic number 367.
This is not magic number. That generally we 367 is this coming from that basic calculation, that head calculation, that raw density and other things calculate, that we generalize this one. This is I will send the calculation. This is, don't worry about that magic number. This is for that density, and this is simplifies the equation, right? That understood, I think, no?
Yeah.
That
So the next question is, what is the maintenance you discussed in the pumps?
maintenance mean that frequently that you have to check the motor motor bearing and alignment, and then you have to clean the motor fan, and then you have to check the pressure and suction pressure and delivery pressure frequently, and greasing. Then monitoring the pumps, then you have to keep the reading head, and always most of the cases they don't know about the operating head, right? Then maintenance, if you go for the maintenance, first check. I have a lot of experience. Then if you go to the site, then I check the running head. Sometimes it is the non-return value is clocked. That people don't know. Sometimes that we are operating the less flow, less efficient, right? Then system, you have to check. Maintenance means not only the pump, also system. You have to check the valve and everything in the suction, non-return, gate valve, pressure gauges, that lot of things. But basically, that after at least for 5 years, you have to that total overhaul the pump and do the needful, right?
Next question is explain the difference between the water pump and the fire pumps.
Right. Generally, I am expert. I am talking about water pumps. That fire pump is same, but that is important one is that gland and that sealing method. That for uh, this gland recommended one is gland for the seal in that water pump. We have seal, that mechanical seal or gland. Then fire pump, it should be gland type. Then that fire pump is that low head operation, and motor capacity should be high. That in that water pumps generally we say 10%, 1.1% more than this motor loading condition should be very that fire pump and sealing method. That fire pump has been the standard to select, I think.
Thank you very much, Mr. Dinesh. The next question is what are the tips you can give to reduce the electricity consumption of some pumps and pressure pumps used in households? What are the tips you can give to reduce the electricity consumption of some pumps and pressure pumps used in households?
Household, then generally household constant head pumps. Like if you select the pump, nothing to worry about. The efficiency is already selected now. Then before you are going to, if you can consider this NS and efficiency before selecting the pump is important, right? After selection of pumps, maintenance is the only one that pressure pump or whatever is maintenance is that put well and non-return well you have to maintain properly. And if that my option is that most of the cases pipe friction is the pipe delivery pipe selection is lower diameter has selected, and pump and demand is not matching. Sometimes 15 then 5 minutes 10 minutes that whole tank is going to fill. That it is that power consumption is very high and pipe diameter is also very less. Then let's say I can explain in diagram. This is system, right? Always you have to keep in mind the system. Then say if the diameter is less, higher diameter, if you select the system is this one. Then your head requirement. Then if you that flow rate is this one. If you select the higher flow rate instead that your less flow rate, right? That you can generally my idea is at least 1 hour we have to fill the tank, but most of the cases pump is oversized. That is energy inefficiency in the household. Right now that we with Sustainable Energy Authority we are preparing energy star rating for the pumps in household application also. Then I think in future you will solve this one that we have star rating for centrifugal pump in near future. Right?
Yeah. Okay, thank you very much. So the next question is, when we have a steep system and we can't reduce friction head further, does it work with series pumping to increase flow? When we have a steep system and we can't reduce friction, we can't reduce friction head further, does it work with series pumping to increase the flow?
That means you have system you have system that steep or something system, but that you want to install the pressure boosting or something, right? Then that's this is the pump curve generally. Then if it is parallel pumping, double pump curve is something like this. If it is series pumping, this head is going something like this. That you can increase the pressure and flow rate also by series pumping. But the thing is that your energy consumption is very high. Instead that if you can change the pipe diameter and reduce the friction, it's better. You can boost, right? You can apply series pump. You can definitely increase the pressure and increase the flow rate also, right? Using the series pumping. But the thing is that pipe friction is very high. Then you are losing your energy by entropy, like friction. Then my opinion is you have to replace the pipe and reduce friction. You can do, right? Series pumping. Understand?
I think, yeah. So I think we are almost, there are a few more questions and we are running short of time. So we'll try to answer all of them,
Okay.
but very short answers. What is the suction and discharge pipe velocity range? What is the suction and discharge pipe velocity range?
Yeah, generally that in water context, I recommend, my recommendation is then suction anyway that point velocity should be more than 0.6 meter per second everywhere in the system, right? But in the suction side, if you can use this one, is better 0.6 for suction. Right, for the delivery, if it is the higher that non-return and other component to work, you have to keep 1.5 meter per second in that pump and non-return, in branch non-return. This is recommended velocity in the non-return. And well, then due to common header, we have to maintain 1 meter per second. This is the norm, I think, for suction side. If it's 0.6 meter per second, therefore the non-return in branch in 1.5 meter per second. For the common header and pump in main, 1 meter per second. I think answer is okay.
Yeah. So we are into the last two questions. So some important factors to be considered has mentioned when considering energy conservation, such as pipe friction, pump efficiency, and so on. please arrange them according to significance, how they affect in Sri Lankan context, considering long term and short term if different.
That means.
So I will repeat the question once again.
Yeah, okay.
Some important factors could be considered as mentioned when considering energy conservation, such as
Right.
pipe friction, pump efficiency, and so on. So the question is to arrange them according to the Sri Lankan context, considering long-term and short-term use.
Yes, that short-term use, you don't worry about the energy conservation. I think I mean that it is say continuous. If it is a continuous pumping, you have to worry about the energy conservation, right? That as I mentioned, that 91% energy is used for running cost if it is the continuous pumping, right? Then if it is say 1 hour or 2 hour pumping per day, then you don't worry about the energy conservation and high efficiency pump. Then you have to worry about the capital cost. If it is the continuous pumping, then you have to worry about the energy efficiency, right? One question about the pump efficiency. Then the system also same, that if you install it is 20 years or 10 years. If it is more than 20 years, then the pipe system, then you have to worry about the pipe diameter, right? Definitely you have to go for higher pipe diameter and 1 meter per second. Then if it's short period, you have to think about the capital cost, right?
The next question is, when water is being pumped to the tower, can we always use a soft starter instead of a VFD?
If it is
When
constant, yeah, if it is constant head pump, then constant flow rate, then constant head, yeah, soft starter, or even if it is low capacity pump, star delta, or then direct online also, doesn't matter, right? But this thing is the starting current is sometimes it is DOL, it is 7 time amperes taken per starting. Then if it is go for soft starter, it's good, right? Now that's almost VFD and soft starter are almost the price is same. I think my according to my understanding.
can two pumps operate at once together parallelly? One VFD, other normal.
That no, that the thing is I can explain here. This is the pump curve, right? Then if it is same pump also, then if it is VFD operate, pump curve is shifted, right? Then if we run parallel, then combined pump curve is something like this, right? Then your system is something like this. Then only that this is the single pump operation. This is VFD. That then sometime that your efficiency is drop due to that this application. That you can control the flow rate, but if VFD pump and uh, other pump is used in parallel, and that actually that small person and big person is fighting, right? Like then it's not suitable. My understanding, but you can use at least for controlling. But better option is both pump have to reduce the speed. Then you have to get that flow rate, right? Then one pump and both pump you can reduce the speed to same frequency. Then this you can use parallel pump to operate. Then that is the optimum efficiency one, right? Understand, I think.
So thank you very much. I will, the final question for this evening would be, please explain insulated bearing for pump application for motor, both sides.
Not both side, that motor application, the insulated bearing is important if you use VFDs, right? VFD, in the case of VFD application, there may be that eddy currents inside the motor due to harmonic, right? Then that in that case, to avoid the bearing failure, we have to use insulated bearing. Then only non-drive end, I think my option is only one bearing. You can use non-drive end, then you can avoid the short circuit. Right? We need not to have both bearing in the motor, but if it is better, you can have that very high price, no, that insulated bearing. Then non-drive end, you can use this insulated bearing for the VFD application. That harmonic filter also the option, but better if you can use the seared bearing in the non-drive end.
So I think that concludes our Q&A session. So thank you very much, Mr. Dinesh, for your very insightful lecture. I'm sure that you shared a lot of practical aspects when it comes to the comes to operating the centrifugal pumps. And thank you very much for providing very good answers to all the questions. I'm sure that it was a very useful session to our participants. And thank you very much. Once again, I hand over the session to Mr. Pasang.
Thank you, Professor. So thanks once again, Mr. Dinesh, for your insightful presentation. It helped us. We learned a lot from this, and thank you very much, Professor Migara, for moderating the Q&A session. And I'm sure the audience had learned a lot from this presentation, and hope see you all in another insightful EMF energy management forum in future. And until then, so good night to you all, and wish you a pleasant evening. Thank you.
Good night.